You know, when you really think about it, beaming high-speed internet from a pizza box-sized dish on your roof to a satellite hundreds of kilometers up in space, it really does feel like magic. But it's not. Today, we're going to pull back the curtain and show you the absolutely incredible engineering that makes Starlink possible. Let's dive in. So, just to give you some perspective on this, that signal from your dish, which people lovingly call Dishy McFlatface, has to travel 550 kilometers, straight up. It has to punch through our entire atmosphere and into the vacuum of space just to reach a Starlink satellite. And get this, that satellite isn't just sitting there waiting for your signal. Oh no, it is whipping across the sky at a blistering 27,000 kilometers per hour. Your little dish has to find and maintain a perfect, solid connection with that tiny, speeding target. So that brings us to the big question, right? How in the world do you create a stable, high-speed connection between a stationary dish and a satellite moving that fast with that much precision? Well, the answer is just amazing. Okay, so before we get to the how, you really got to understand just how big of a challenge this is. Because Starlink isn't just a souped-up version of your old satellite TV dish. No, it's a completely different animal. Just look at the difference here. Your TV dish, it's just a passive receiver. It sits there and listens for a super wide signal from a giant satellite that's way up at 35,000 kilometers. But Starlink has to both send and receive data, and it's doing it with a satellite that's 60 times closer. Now that low orbit is awesome for reducing latency, that dreaded lag that gamers absolutely hate. But it also creates this insane tracking problem we're about to solve. So, you might be thinking, okay, Dishy must have some crazy fast motors inside, right? Constantly swiveling around? But no, that's not it at all. Any mechanical part trying to move that fast, that constantly, would just burn out in a few weeks. The real secret is silent, it has no moving parts, it's all in the microchips. All right, let's pop the hood on Dishy McFlatface and see what's really going on in there. You won't find any gears or spinning motors for tracking. What you will find is a total marvel of electronic engineering. What you're looking at is basically one giant circuit board, and it is packed with hundreds of specialized microchips. All of them are wired to this wild hexagonal grid of, get this, 1,280 tiny individual antennas. Yeah, 1,280 of them, all working together in perfect harmony. And this whole setup, this grid of antennas and chips, has a name. It's called a phased array. And it's the key to everything. It's a piece of tech that lets you form and then steer a beam of radio waves with incredible precision, using nothing but electronics, no moving parts. This is where the real magic happens. Okay, so the first big problem this array has to solve is power. I mean, how do you get a strong enough signal from your little dish all the way up into orbit? Well, you do it by combining the power of all those tiny antennas into one single, powerful, focused beam.
If you just took one of those 1,280 antennas by itself, it would be pretty useless. Its signal is super weak, and it just kind of radiates out in every direction, like a really dim light bulb. You'd never see that from space. But when you get a whole bunch of them working together, something really cool happens with the radio waves they send out. Where the waves line up perfectly, they add up and get way, way stronger. That's called constructive interference. And where they don't line up, well, they just cancel each other out.
So now, imagine doing that, but with all 1,280 antennas. By making them all fire at the exact same time in perfect sync, you create this massive area of constructive interference. All that energy gets funneled into one super tight, powerful beam that shoots straight up. It's almost like a laser beam made of radio waves. And the result is just mind-blowing. The beam isn't just 1,280 times stronger. No, because of that intense focusing effect, the phased array makes the beam's effective power a staggering 3,500 times greater. And that is more than enough punch to get to orbit. Okay, so we've got our super powerful beam. Awesome. But how do you aim it at a target that's screaming across the sky at 27,000 kilometers per hour? Especially when you've got zero moving parts. Well, the secret here is something called a phase shift. And really, it's all about timing. Instead of blasting the signal out of every antenna at the exact same moment, the software intentionally introduces these tiny, tiny calculated delays to each one. Here's how it works. See? If all the antennas fire at once, what we call in phase, with no delays, you get a beam that goes straight up. But
If you start adding a microscopic delay to the signal going to the next antenna and a slightly bigger one to the one after that, and so on, the whole wave front starts to tilt. You are literally steering a beam of pure energy just by playing with the timing. It's genius.
And this is all happening at an incredible speed. The dish's software is constantly crunching numbers. It knows where it is thanks to GPS, it knows the satellite's exact orbital path, and it is recalculating the perfect delay for all 1280 antennas, updating the beam's direction every few microseconds to make sure it stays perfectly locked on.
All right, so we have a powerful beam. We can steer it without any moving parts. It's locked onto a satellite. But how does that beam actually carry, your Netflix stream? Well, it does that by speaking a kind of secret language that's written right into the radio wave itself.
It's a bit of a fancy name, Quadrature Amplitude Modulation, or QAM for short. But the idea is pretty straightforward. Instead of just sending a plain old radio wave, the system is constantly changing two things about that wave. Its amplitude, which is just how strong it is, and its phase, which is that precise timing we were just talking about.
Think of it like this. Every unique combination of strength and timing is like a different letter in an alphabet. For instance, a wave with, say, 59% strength and a timing shift of 121 degrees could stand for the binary code 01101. Starlink uses 64 of these different symbols, which lets it pack 6 bits of data into every single pulse of the wave.
And when I say fast, I mean fast. The dish sends about 90 million of these symbols every single second. You do the math on that, 90 million symbols times 6 bits of data each, and you get a theoretical speed of 540 million bits per second. That is how you get true broadband speed from the sky. Okay, just one last little technical detail for you. The antennas can't send and receive at the exact same time, so they have to split their time. As you can see, the huge majority of the time, about 93%, is spent on downloading data to you. Which makes sense, right? That's most of what we do online. And the other 7% of the time is for uploading your requests back up to space.
So there you have it. From combining 128 antennas into one powerful beam, to steering it with nothing but math and timing, to encoding data right into the wave itself, that's the engineering that makes Starlink work. It's a technology that is already lighting up some of the most remote corners of our planet. And that leaves us with one big question to think about. Now that we have the power to connect literally anyone, anywhere, what are we going to do with it?